in Johannesburg.
I can see it there, right? Okay, perfect. I think everybody can listen to me. And hello, everyone. I'm Saumik Samanta. I'm a lecturer at Wits University, School of Geoscience. So professionally, I'm an environmental and analytical geochemist. And my research interest is to understand the sources and cycling of different trace metals, particularly heavy metal in different environmental reservoirs. And in this study, I actually focused atmosphere as a reservoir. So I just wanted to see how the particularly heavy metal, which is toxic in nature, comes to the atmosphere and how it actually, what is the fate of these elements and what is the toxic effect it actually produces. Before I start my topic, I just want to show some of my previous work, two of my previous work, which is in line with the previous speaker who spoke about the emissions from road, which is very important. This is one of the study which I did based on the fact that the lead contamination, because you know that few decades back we have a lead contamination due to leaded petroleum. But after that, the entire world has phased out lead additives from petroleum. But instead of that, if you focus the global south, particularly India, Thailand, South Africa, the lead toxicity is still there. So to understand that, I just made a model simulations based on isotope data, and that find me out that actually the bituminous road, which is throughout this country, is one of the prime source of lead in atmosphere. So the more vehicle is increasing in the country or in this area, the more chance to get road-related emissions, particularly heavy metals such as lead. Okay, so, and next another studies I actually also did on lead. Lead is also one of my favorite elements. I did actually to understand actually how lead has been transferred from one ocean to another oceans. And in this study, I showed that actually how the lead from South Africa has been deposited in Indian Ocean, and later it transported to the other ocean, Atlantic Ocean, which is an important fishing ground as well. So, but it also sources everything from lead. And last year I moved to Joburg, and once I moved to Joburg, I just surprised to see this figure that the PM 2.5 particle in Joburg air is always above the WHO limit. And if you see the winter season, particularly May to July, and it's maximum. So, but we do not have actually a lot of information about what's the chemical composition of this atmospheric particulate matter, 2.5 or 2. PM10 particle. What's the chemical composition? Particularly, what about the inventory of the heavy metals such as lead, chromium, cadmium, arsenic, mercury? So this is actually a big question. And in South Africa, there are few studies happened regarding the heavy metal in atmosphere, and mostly the University of Northwest, University of Pretoria have involved in the studies, but mostly happened in the northern provinces, and still the data set is very limited, and also we do not have the information, the fractions of toxicity from each element. So for example, if we have high concentration of chromium in atmosphere, it doesn't mean all the chromium is toxic. How much? Is 40% of chromium is toxic or 90%? That is some of the information we need to know before we decide the ultimate fate. And particularly in Johannesburg air, there is almost no data available. In my knowledge, there is no data available. However, if you see, there is actually one of the survey happened in last year, Environmental Infrastructure Services Department, and they said surveyed over 50,000 Joburg people and find that 90% of the Joburg population is concerned about what they are breathing. But we do not have any answer. Therefore, but the fact is actually there is some reason why there is so much limited atmospheric chemical composition is available, because we need to have clean sampling technique, which is actually needs to be adapted because the concentration of metals in atmosphere is low. But for that, actually, the sampling should be done in a clean sampling way. And of course, after the sampling, it needs to be preserved properly. And to process the sample, we need to have an ultra-clean laboratory, which most of the places doesn't have. And on top of that, we need to have the advanced mass spectrometer facilities, for example, ICP-MS, multiple collector ICP-MS, to measure the concentrations as low as parts per trillion. Okay. So therefore, I welcome you to WITS Earth Observatory, where we have a very good facilities to work on ultra-trace clean level of concentration. So we have the clean lab, class 100 clean lab, where the filtered air comes through, which prevent the contaminations, unwanted contaminations, as well as we have the mass spectrometer, which can detect the metal concentration as low as parts per trillion. But also, we can also able to measure the isotopic composition of some of the metals, which is great for begin the isotopic studies. Okay, so that's why actually I started the studies, and the aim and objective is to understand the seasonal variability of the airborne heavy metals. So I just tried to see, because these are the few data I'll be showing today. And also I try to see the toxicity, that means the solubility of these metals, so which is very important to understand the toxic effect. And also after that forward, I'll study some of the isotopic systems in order to understand the source quantitatively, how much fractions come from different source material. And of course, is actually, as these region, Johannesburg region is actually located in the northern province, close to the northern provinces. So the effect of mining and post-mining activities are there. So I just wanted to understand how much the airborne material comes from those northern provinces. Okay. So for that, I just adapted two sampling strategy. As you can see in the left-hand side, this is one of the strategy where I can collect the total atmospheric particulate matter. You can see that there is a commercially available aerosol sampler in which the filter paper, cellulose filter paper is installed. And that filter paper is connected to a vacuum pump, which is oil-free vacuum pump. And I just started the sampling from the rooftop of School of Geosciences, Wits University. And you can see one of the diagram, the filter paper where the dust is accumulated, and you can see nice dark brown color of the dust, which is not good to see, but it's really good for the chemical analysis. At least we have a lot of samples. So, and before and after we use the filter paper, we take the weigh so that how much dust is accumulated we can measure. And the right-hand side, you see this is the mini volume sampler. And from this sampler, we can able to collect the particularly PM10 or PM2.5 particles, which is another attractions of scientists. Okay. So let me go to the result. So this is the red dots. What you can see is actually the result from my study, is actually the total atmospheric particulate matter concentrations in Johannesburg since July 2025 to last month. And the sampling is still going on. And what you can see is actually, and the blue is actually from the observation station at Alexandria. So what is the noticeable thing? There is a little difference between these two sites. And one of the things could be that the Wits University is located very close to the center of the city. So there might be some local sources, localized sources. But another interesting fact is actually due to rainfall, the atmospheric particulate matter dropped because there is a rainfall happened between 22nd and 27th of July. And that actually reduces the atmospheric particulate concentration. So rain is necessary for us. So now we are actually I'm going to show you the chemical composition of the dust particle that I have collected. So for that actually, as I said, actually we need to follow some of the rules, and for processing whatever we used, all the reagents are ultra pure grade, all the plastic lavers are acid cleaned, and all steps conducted under laminar flow so that any kind of unwanted contamination may not happen and not affected our result. And each steps I did a blank, which is very important term of chemistry, and we subtracted that value with the samples. Okay. In the first step, what I did actually, I leach out the toxic fractions. So you can see the filter paper using a plastic forceps. I put the filter paper in a centrifuge tube, blue cap, what you can see, and I add 1 normal ammonium acetate. This is a traditional recipe, and I leave it for the reactions, which these reactions leach out the toxic fractions of component to the ammonium acetate solution. So after that, we separate that solutions to get the concentration of the toxic matter. And then after that, I put that filter paper, which is remaining, I just put it in a Savilex vial for the total digestion. And it actually dissolved the entire filter paper. So in the first step, we got the toxic content, which we also tell at soluble fractions. After that, the remaining fractions is dissolved. So by this process, we can actually have the toxic concentration as well as the total concentration. Let me show you some of the result. So this is actually the concentration. The black bar is actually the soluble content, which is, we call it as this toxic content, and the gray is the total. Okay. So particularly if in the right-hand side diagram for where you can see the trace metals, heavy metals, you can see that actually the concentration of chromium, copper, zinc, barium, and lead are really high. And particularly if you see the soluble concentration in chromium and zinc, it's really high. But this is just a concentration. We have to see this concentration based on some background. So therefore, we just did the enrichment factor based on the sample concentration and normalize with the concentration of upper continental crust. And from that, we can actually predict what are the anthropogenic sources. And once the enrichment factor is more than 5, we can tell that it's actually strong anthropogenic process is playing a great role. And for that, you can see chromium, copper, zinc, arsenic, and lead. These are actually showing the signal of real anthropogenic signal. But what are the sources? To understand that, I just plotted the solubility in the same graph. And here, let us understand one by one. Let's focus on chromium, which is actually high solubility. Let me speak a little bit on the chromium chemistry. So chromium has two states charge. One is +3, which is insoluble, +6 is soluble. Okay. So you know that actually in South Africa is the biggest producer of chromium from Bosveld mine, but in mine it is in +3 state. But once it is processed through the ferrochrome production, which is a high temperature process, the +3 chromium is transformed to +6, which is soluble and toxic. And in Joburg here, what we see is actually very much toxic chromium is there. So this is one of the big outcomes from this study, but this is only one data, so we have to work on more. So I just want to quickly tell other things. Here, if you focus on arsenic, arsenic is exactly opposite compared to chromium. The +5 arsenic is insoluble. And here you can see the solubility of arsenic is low. So from that, we can say that actually some high temperature process which can actually oxidize the arsenic is probably the source, and it could be the power plant. Next is actually, let's see the lead. Lead solubility is also low, but the lead enrichment factor is high. So what could be the prominent process? It's, of course, not some high temperature process, because high temperature process have generally increased the solubility. So we can actually tell about some low temperature process, which could be the road material, what I just spoke in the beginning of my talk. And in Joburg is actually a lot of vehicle around, so could be because this is of the road material, the abrasion of the road material. And there is two things I would like to show, that zinc has actually high solubility, but copper has low solubility. So of course the sources are different. One is high temperature source, one is low temperature source. So this is the beginning of the study, so I do not have more conclusion from now. But also I actually checked the air mass trajectory, back trajectories, which also show that actually the air mass is coming from this Mpumalanga, Northwest, all those provinces, and bringing all those shops and mining product. So what we find is actually there is a lot of mining influence in the city atmosphere, but we also have to see the other data, how it happens. So the more data will be coming out and more information we'll get. So at the end, so the next step would be to understand the temporal variability of the chemical composition of atmospheric particulate matter. At the same time, I would like to collect more samples from mining regions, some remote villages to understand the difference, and it also actually help us to understand the source environment. Road dust is another important factor. And of course, at the end, I'm interested to do some isotopic studies in order to say the quantitative information rather than qualitative, which is important for the policymaker, I guess. Thank you very much. I think I'm over time.